Yeah, so good morning to all. So in the previous lecture, one of the students mentioned that there was a typo regarding this formula. So actually, in this equation, we have considered in the statement of theorem that y double dash plus pxy dash plus qxy is equals to 0. But on the other hand, in this part, I have considered y double dash plus qx y1 dash plus rx y1 is 0. So I have corrected this thing according to the this particular equation. When coefficient of y dash is p and coefficient of y is q, so that means we get these two equation, and then we substitute it here. Instead of cancelling out rx function, the qx function will cancel out, and here we'll get the function p. So what is p? P is essentially the coefficient of y dash term, right? And therefore this linear differential equation has the solution in terms of p function instead of q function, right? So because I have taken here some wrong equation last time, so now I have corrected this one. So I will share this PDF today again, so just go through it once again, right? Okay, so using this particular result, we are getting as an application that we will be using in this lecture also. So that is essentially whenever two functions, two solutions y1 and y2 of given second order homogeneous equation are linearly independent, whenever Wronskian is non-zero for some point in the interval, right? So this result we derived from the previous result, which says that Wronskian is 0 at particular point if and only if Wronskian is 0 everywhere in the interval. And the same result says that Wronskian is non-zero at a particular point if and only if Wronskian is non-zero at every point in the interval, right? So just remember that y1 and y2 are linearly independent if and only if Wronskian is non-zero at a particular point. So that only thing we need to check is Wronskian is non-zero to conclude the linearly independence. Yeah. So so there are two certain method to solve the second order linear differential equation with the constant coefficients. So we have discussed that whenever we have such a linear differential equation with constant coefficient, only thing we need to check is we need to find the solution of the corresponding polynomial. So that polynomial is this one, right? am square plus bm plus c is equals to 0. So let us write down this remark that to find solutions of the differential equation ay double dash plus by dash plus cy is equals to 0, we need to solve the corresponding quadratic equation, and that is am square plus bm plus c is equals to 0, right? So depending on what are the solution of this quadratic polynomial, so we know that whenever we have a quadratic polynomial, we can solve it using the coefficient as the solution is minus b plus or minus b square minus 4ac divided by 2a. And here using this discriminant, we can divide into three parts. So first part is distinct roots, distinct real roots, same real roots, and the complex real root. Right. So there are three cases. So let us start with depending on these two values, the solution will be yx is equals to, so first solution will be m1x if m1 is solution, one solution, and second solution is e power m2x. All right. So depending on what is the solution of this quadratic equation, we will get corresponding solution of the corresponding differential equation. So let us discuss first case in which we have distinct solutions of the given differential equation. So suppose m1 and m2, so let us call this differential equation 1, right? m2 are two distinct real solutions of equation 1, right? So this is our first case. So whenever we have two distinct real solutions of this quadratic polynomial, corresponding solution we get yx is equals to e power m1x, and second solution we'll get is e power m2x. Of the given differential equation. So what is the given differential equation? That is ay double dash plus by dash plus cy is equals to 0. Right. So why it is happening? Because we have computed that whenever we have, if y satisfies the differential equation, that gives us this term will be 0, and this term is 0 if and only if the polynomial is 0. Right. So therefore solving this linear differential equation is correspondingly solving the binomial, the quadratic polynomial, and that gives us this. So now we got two solutions. The question is whether these two solutions are independent or not. So to check whether y1 and y2 are independent or not, we shall find. So there are two ways to checking whether the solutions are independent or not. Either we can use the direct definition or we can use the Wronskian. So mostly we will be using the Wronskian itself. So we shall find the Wronskian. Yeah, so what is the Wronskian here? Wronskian here is Wronskian of y1 and y2. That is y1, y2, y1 dash, y2 dash, and y1 is e power mx, m1x. This example is e power m2x. Its derivative is m1 e power m1x. Derivative of the second function y2 is m2 e power m2x, right? And then whenever we find this determinant, we can easily see that this determinant is m2 minus m1 times e power m1x into e power m2x. So that means it is m1 plus m2x, right? And then we know that this function will never be 0. So it depends on whether this term is 0 or not, right? M2 minus M1. And what is our first case? Our first case is that this polynomial am square plus bm plus c has two distinct real solutions, m1 and m2, right? So that means in this first case, m1 is not equal to m2. Yeah, so since m1 is not equal to m2, this is non-zero. So whenever we have two distinct real roots of the given of this corresponding quadratic polynomial, we will get the independent solutions. So therefore, the solutions y1 and y2 in this case are independent. Yeah, so let us see one example. So consider we want to solve the differential equation d square y minus dy is equals to 0, right? So same equation we can also write as d square minus d y is equals to 0. So whenever we are solving such a differential equation, means since it is a second order differential equation, we need to find the two solutions which is independent. The same way, like where we have a system of two linear equation, the solution space has two independent solutions. The same way here, we have, yeah, so that depends actually if the linear equation is whether the determinant is non-zero, etc. So here also our goal is to find two independent solutions if they exist. Yeah. So what is this equation? First of all, we know that d is d square is in our notation d square by dx square, and d is d by dx. So therefore, essentially, we are solving the equation y double dash minus y dash equals to 0. We want to solve this equation. So therefore, the corresponding quadratic polynomial or binomial is, so what will be the corresponding binomial? It will be 1 times m square, so that is m square minus 1 times m is equals to 0, right? So this will be the corresponding polynomial. And yeah, so polynomial is m square minus m, but what we are going to do is we are going to solve this polynomial. So the roots of m square minus m is equals to 0, the solution of m square minus m is equals to 0 are, yeah, so we can simply find this is the simplest polynomial. So we know that one solution is m1 is 0 and other solution is 1, right? Yeah, so now we can see that this is our first case, right? Because m1 and m2 are real solutions of this quadratic binomial and they are distinct. So therefore, we get independent solutions. So what are the solutions? Solutions is yx equals to e power m1x, and m1 is 0. So that means it is e power 0 is 1. So this is identically one function. And the second function is e power m2 x, that is e power x. So we got these two solutions constant function 1 and e power x function, which are independent solutions of the given differential equation. So what is important in this differential equation is that it is a homogeneous differential equation, and the coefficient of y dash and y double dash are constant, right? Otherwise we cannot apply this method. Okay, so let us go for the second case. So second case is, yeah, any doubt? Okay, so second case is that whenever we have distinct, we have same real roots. So that means basically m1 is equals to m2 of the quadratic polynomial. Yeah, so in this case, what to do? So here we know that the first solution we can get is y1x equals to e power m1x. But second function, if we find, it will be e power m2x, but m2 is equals to m1. That means essentially we are getting y1 function itself, right? So in this quest, yeah. So yeah. So here in the previous example, I forgot to write the general solution. So we got two functions, y1 and y2. And we need to write down the general solution of this differential equation. So general vector, we know that we can write as a linear combination. So that means the general solution is constant times first function, that is 1, plus second constant times second function, that is e power x. So general solution is c1 plus c2 e power x, where c1 and c2 are constant. Right. So every time we will also write down the general solution in all these three cases. Yeah. So here, how to find the second function? So this method is known as order of reduction method. Yeah. Any doubt? So order of reduction method, we shall be using here to find the another solution. So what we'll do here is, suppose so this method is known as reduction of order method. So we use reduction of order method to find other solution. Yeah, so what does this mean? This means that we know what first solution. To find the second solution, we will reduce the second order differential equation into first order differential equation. So what we'll do is we will substitute. So this method is similar to the variation of parameter method. So substitute the function which we are looking for is vx times y1x. Yeah. So this function is v1 times y1x. and we know that y1x is the function. Let us say it is uh, instead of m1x we simply take yeah, so let us take is e power m1x or e power mx. So in this case, what will be y2 dash? Y2 dash will be v dash e power m1x plus m1 e power m1x vx, right? And that is nothing but v dash plus m1v times e power m1x. So we got first derivative of this y2 function. So again, what we are going to do, we will identify vx here also. So to identify vx, we will substitute y2, y2 dash, and y2 double dash in the given differential equation. Yeah, so here if we differentiate the first term, we get v double dash plus m1 v dash e power m1x plus m1 v dash plus m1 square. Uh, yes, this times e power m1x. So essentially, what is this? This is v double dash times 2m1 v dash plus m1 square v times e power m1x. So we got y2 double dash also. We know y2 dash and we know y2. Y2 is the substitution. So we are assuming that y2 is a solution of this given differential equation, right? So if y2 is solution of the given equation, what is given equation? That is a y double dash plus by dash plus cy is equals to 0. So if y2 is this solution, that means a y2 double dash plus by2 dash plus cy2 is 0. And then substituting all these values, what we'll get is a times v double dash plus 2m1 v dash m1 square v e power m1x plus b times y2 dash, and y2 dash is v dash e power m1x plus m1v e power mx plus c times y2, and y2 is v times e power m1x is equals to 0. So now from this equation, obviously we can take e power m1x common, and then e power m1x is a non-zero function. We can cancel out that function. So that means essentially we get a polynomial a v double dash plus 2am plus b v dash m1 plus a m1 square b m1 plus c times v is equals to 0, right? And then what we know is, we know that m1 and m2 are two solutions of this equation, right? So since m1 and m2 are equal, m1 satisfies uh, not only this equation am square plus bm plus c is equals to 0, it is also solution of, so whenever we have repeated roots, we know that it's a solution of the derivative of the equation. So derivative of this equation is 2am plus b is equals to 0. So m1 is solution of this equation. That means 2am1 plus b is equals to 0, and that will give us m1 is equals to minus b by 2a. Right. So m1 satisfies this quadratic equation and it satisfies this equation also. That means this term is 0 as well as this term is 0. Right. So let us call this equation number 1. So using am1 square plus bm1 plus c is equals to 0 and m1 is equals to minus b by 2a, from 1 we get, from equation 1 we get yeah, so we get only one non-zero term, this one, right? So we get a v double dash to be 0, and since this is a second order differential equation, we can assume that the coefficient of v double dash is non-zero. That means a is non-zero. So finally we get v double dash is 0, right? And so what are the solution of this equation? So for that we need to integrate it. Whenever we integrate it, we get v dash equals to constant. Yes, yeah. And then uh, so what can be this? Yeah, so and then what will be the next? We will be, let us call this c1. So the integral will be c1x plus c2, right? Yeah, so now we can use certain initial condition. So what is the initial condition did we use? Yeah, so that depends on what initial condition we are choosing. So here we have chosen the initial condition to be arbitrary. In the corollary of this, where we discuss uniqueness, we consider the initial condition to be this one, right? So it depends the solution on the initial condition. Yeah, so suppose we take this general condition, then the general solution will be what? The general solution will be this v, but as a special condition, if we choose certain condition, then uh, in a special case, we get one of such vx function to be x, right? So basically we are, among these all infinitely many curves, we are choosing a special curve, that is vx, and this special choice that will gives us y2 function. What is y2 function? Vx times e power m1x, right? So as a special case we get this function, right? So every time which special function we are taking, that depends on what is the initial condition given. But if it is not given, we can choose any special function and we can find corresponding y2, and then we can check that whether this y1 and y2 satisfies this Wronskian condition or not. Yeah, so the Wronskian in this case is y1 y2 y1 dash y2 dash, and that will be, so first function is e power m1x, x e power m1x, and then the derivative of this is m1 e power m1x. Derivative of this will be two terms, e power m1x plus m1x e power m1x. All right. So yeah. So what will be this determinant? This will be e power m1 x. We can take common from the first term. So this will be 1 m1 x e power m1x yeah. So this will be now e power m1x. What will be this? E power m1x plus m1x e power m1x minus x m1 e power m1x. Yeah, so these two terms will cancel out. Finally, we get e power m1 square x. And we know that this function is always non-zero function. Right. So therefore, the solution is y1 and y2 are
Sir, how it is e raised to the power m1 square x?
Sir,
okay. So you are right. So it should be 2 times, right? Yeah.
but sir, we have taken common now.
Yeah. So it is e power m1x into e power m1x. So power will add up. So that will be m1 plus m1x plus m1x. So it is 2 times m1x.
Sir, sir, please roll up, sir.
Yes.
Okay, sir. From first column, we have taken
We have taken
common.
e power m1x common. Yes.
Okay, sir.
Right. So okay. So y1 and y2 are linearly independent because of this Wronskian condition. Yes. So yeah. So in this case also we will write down the general solution. Will be yx is equals to c1 y1x plus c2 y2x, and that will be yeah. So don't confuse with c1 c2. I think we have taken it earlier also here, so we can call it dash otherwise. So this will be c1 times e power m1x plus c2 x e power m2x. Yeah, so we can club this e power mx term and we can rewrite it in this form also. So this is m1. Yeah. So this is general solution whenever the roots are same. Roots of the binomial are same. And then we have a third case, which is the last case in which we have complex roots. So whenever we have a complex, the roots are complex numbers. Only thing will change is essentially what is the solution. So that thing will change. So third case is if the solution, if the roots are complex conjugate. So that means discriminant is non-zero, and that gives complex numbers. Yeah. So roots means roots of quadratic binomial a m square plus bm plus c are complex conjugate. In this case, let us call that, suppose the first root is the complex number alpha plus I beta, and second is conjugate of this, that means alpha minus I beta. And since the roots are distinct, we have already verified that e power m1x and e power m2x are independent solution, right? So since m1 is not equals to m2, e power m1x and e power m2x are independent solutions. Yeah, but here what happens is whenever we'll consider this e power m1x, so that is e power alpha plus I beta, that is actually function of complex number. So instead of getting a solution which is a function of complex number, we should look at the solution uh, which is a real function. So let us call it capital Y1. This will be capital Y2 function. And using these complex functions, which is a solution, we are looking at the real solution. So we know how to find the real part of the complex number. The same way we'll do here. So what we'll do is consider y1 to be, so real part is y1 plus y2 by 2, right? And imaginary part is of a complex number is y1 minus y2 upon 2 times I. So the way we are finding real and complex part of complex number, the same way we can find real and complex part of the complex number, complex function also. So let us check whether this y1 and y2 are Li or not. Right. So again, here also we can use the Wronskian method. So here the Wronskian of y1 and y2 divided by y1 dash y2 dash will be nothing but y1 plus y2 by 2 y1 minus y2 by 2I divided by y1 dash plus y2 dash by 2 y1 dash minus y2 dash by 2I. Right. So this determinant, so whenever we solve it, some of, yes, so let us solve it. So it is y1 plus y2 times y1 dash minus y2 dash divided by 4I minus y1 minus y2 and y1 dash plus y2 dash divided by 4I, and then some of the terms will cancel out. You can expand this. Essentially, finally, what we'll get is minus 2 times y1 y2 dash plus 2 times y2 y1 dash divided by 4I. Right. So you can easily expand this and we can check this happens, and this last term whatever we can see is in terms of the Wronskian of y1 and y2, right? So since, so what is this? This is Wronskian of small y1 y2, so that we are getting in terms of Wronskian of the capital y1 y2. So since y1 and y2 is Li solution, Wronskian of y1 y2 is non-zero, and that is this term in terms of Wronskian of y1 y2. What we'll get is Wronskian of small y1 y2 is also non-zero. So that means small y1 y2 is Li. Yeah, so essentially this the general solution in this case will be yx equals to c1 y1x plus c2y2x, and that is c1 times the real part of this complex function e power alpha plus I beta. So in this case, what we'll get is the first function we'll get is e power alpha x times the real part. Real part is cos beta x, right? And plus we'll get c2 times e power alpha x, the imaginary part. Imaginary part is sin beta x. So finally, what we get is e power alpha x common c1 cos beta x plus c2 sin beta x. Right, so this is general solution. Yeah. So once again, let us go through this method once again. So we assume that we have roots of this binomial which are complex conjugate. So complex conjugates are the root is alpha plus I beta and alpha minus I beta. So whenever we have this case, the solution will be e power alpha x plus constant times c1 cos beta x plus c2 sin beta x. So the second, yeah, so let us take one example of this type. So we want to solve the differential equation d square minus 2d plus 5 times y is equals to 0. Right. So in this case, we have the differential equation. We shall solve y double dash minus 2y dash plus 5y is equals to 0. So corresponding binomial will be yeah. So corresponding polynomial, what will get quadratic polynomial, that will be m square minus 2m plus 5 is 0. Right. Yeah, and then we'll find the roots of this binomial. So note that we get the values of m are m1 is equals to 1 plus 2i, m2 is 1 minus 2i. So that means basically alpha is 1 and beta is 2. Right. So therefore general solution is yx is equals to e power alpha x. Alpha is 1. So that means e power x first constant times cos beta x. Beta is 2 plus c2 times sin beta x. Right. So by discussing these three cases, we will be able to find the general solution. So let me give an exercise. So the second case uh, we did not discuss any example. So you may write down solution of the equation y double dash minus 2y dash plus y is 0. So uh, let us check whether you can check whether this is second case, first case, or third case. And in this case, write down the general solution. Yeah, so let me stop here today lecture.